Vectors. A vector quantity is a quantity with a magnitude, or a fancy way of saying that is with a size and a direction. On an xy plane, we represent a vector as a directed line segment, or a ray, that starts at point P and ends at point Q. And the notation that we use for vectors is we have this P to Q with an arrow above it. And P is the initial point and Q is the terminal point. So if I take a look at the vector that's sketched here, I have my initial point P, my terminal point Q, and I can see the end of the ray over at the terminal point Q. So a vector quantity has both a magnitude, or a size, and a direction. So the reason why we use a ray is because the length of the ray is the size, and which way the arrow is pointing is the direction. A position vector. When a vector has initial point at the origin, 0, 0, and its terminal point at some point AB, we call it a position vector. And the notation we're going to use for that position vector is U equals, and we're going to have angle brackets AB. So the terminal point values go inside of the angle brackets. So when we see this notation, we know that we have a vector that starts at the origin 0, 0 and ends at a specific coordinate point A, B. Now regarding this position vector u, we're interested in its magnitude, which looks like the vector u inside of these bars. So the magnitude is, of course, the length. So if I see here, I've actually constructed a right triangle. So to find the length of the hypotenuse, what we're doing is we're using the Pythagorean theorem. So the magnitude of u is the length of this vector. So the magnitude of u squared equals a squared plus b squared. So that's the two side lengths squared. So I'm interested in just the magnitude of u, so I'm going to take the square root of both sides, and technically plus or minus comes out, but since we're interested in the length, the formula for the magnitude is just the square root of a squared plus b squared. And now we're interested in what's called the direction angle, theta. So theta here, this direction angle for this specific vector u, is found by using tangent theta equals b over a. So I'm interested in finding theta. I have its opposite side and its adjacent side, so I'm going to use the tangent function. And I have to use my knowledge of what quadrant u is in, so that I can make theta between 0 and 360 degrees, depending on what quadrant my position vector is located. So note, theta equals tan inverse of b over a is simply the reference angle, and we still must think about the quadrant of theta to find our actual direction angle. Alright, in this example, we want to graph u equals the position vector -1, 3, and find the magnitude of u. Remember, this is not absolute value, so this is magnitude when it's around a vector, and its direction angle. And then we'll sketch another vector that is equal to u. So there's a few different things we're doing here. We're going to start by graphing this position vector. Since it's in angle brackets, we have to know that it does start at the origin. So I'm going to go ahead and start at the origin, and its terminal point is going to be at -1, 3. So I'm going to go ahead and go to -1, 3 up here, and instead of drawing a point, I'm going to draw an arrowhead, because that's where my vector is going to end. So this right here is my vector u. So I'm going to go ahead and draw it with a u with a little arrow above it, because we don't draw in bold, or we don't write in boldface. So the way that we're going to indicate this is a vector is with a little arrow above it. So this is vector u, and I'm interested in finding its length. So find the magnitude of u. So the magnitude of u has a formula. So it is the square root of each of the components squared. So each of these parts here squared. So we're going to have negative 1 squared plus 3 squared, or just 1 plus 9, so we're going to have the square root of 10. So the length of this vector is the square root of 10. And now we're interested in its direction angle. So its direction angle is the angle in standard position, so from the x-axis, whose terminal side is the vector. So we are looking for this angle here. This is my direction angle theta. So it's navigating me to my vector. So I'm going to use the relationship tan theta is equal to b over a. So the b value is 3 and the a value is negative 1. So tangent theta equals 3 over negative 1. But this is just going to give me a reference angle. So I have tangent theta equals negative 3, or theta equals tan inverse of negative 3. So if I were to substitute this into my calculator, because this is not a value I can evaluate without a calculator, I would get approximately negative 72 degrees. So the reason for that is because tan inverse, of course, only gives us values in quadrants 1 and 4. So this negative 72 degrees here is actually down here. So, whoops, that got a little crooked. So it's actually navigating me down here. That's negative 72 degrees. But essentially what it's given me is the reference angle if I ignore the negative. So it has given me this angle right here is 72 degrees. So if I'm interested in finding theta, I'm going to take theta to be 180 minus 72 degrees. So the actual value of my reference angle is approximately 180 minus 72 degrees, which is 108 degrees. So that is my direction angle for this vector u. So it had to be between 90 and 180. I'm trying to navigate to this position vector. And now what we're going to go ahead and do finally is sketch another vector that is equal to u. Sketch another vector that is equal to u. So we know that two vectors are equal if they have the same magnitude or same length and they have the same direction angle. They point in the same direction. So we can go ahead and draw another vector, really anywhere else, that points in the same direction and has the same length. So I'm just going to arbitrarily come over here and start it at 2 and end it over here at this point, 1, 3. So this vector that I have just sketched is equal to my vector u because, again, it's the same length and points in the same direction. So essentially, we are allowed to take any vector and move it wherever we want on the xy plane, but the most convenient place for it to be is starting at the origin. So that's why we mostly deal with position vectors. So we can ideally take any vector that's anywhere. So I'm going to draw yet another vector that's equal to u. I'm going to draw it down here. So this is another vector that's equal to u. So we could take any vector and just pick it up and move it so that its initial point is at the origin. And then it's much easier to work with in terms of finding its magnitude and finding its direction angle. We can also perform operations on vectors. We can do addition and scalar multiplication algebraically. So what does that mean if I have a vector v, so this is a position vector, it's in angle brackets, ab, and another position vector w with value cd, and k is a scalar. Well, if I wanted to add those vectors, we would do kind of exactly what you think we would do. We add the first components and we add the second components, as you can see here. So a plus c, comma b plus d. So the answer is still a vector. When we add two vectors, we get a vector. And when we subtract, we again do exactly what we might think we do. We subtract the first coordinate and subtract the second coordinate, or we call them components. And when we multiply by a scalar, remember a scalar is just a number, well, that number would multiply by the first component and by the second component. And the same thing applies if I multiply by a negative. That negative would multiply to the first and second component. So now let's go ahead and practice this. I have a position vector A and a position vector B here. We want to find algebraically, well, what is A plus B? So what we're doing here is we're adding 2, -3 plus 1, 2, or we're adding the first components to get 3 and adding the second components to get -1. And that's it. That is the sum of these two vectors. If I have 2 times the vector A, well, that's 2 times the vector 2, -3, and that 2 gets multiplied to each component, so we have 4, -6. And then finally we can go ahead and think about -b, so that negative would apply to my position vector 1, 2, and become -1, -2. So pretty straightforward rules in terms of the operation of addition and scalar multiplication on my position vectors. Now let's break down the horizontal and vertical components. The horizontal and vertical components are A and B, respectively, of a vector u, a position vector u, with A and B inside the angle bracket. So we call the first value the horizontal component, and B, the second value, the vertical component. So in order to find the horizontal and vertical component, if we have the magnitude, so if we have the magnitude of the vector and we have the direction angle, we can find the horizontal and vertical components, A and B, by taking the magnitude times cosine of the direction angle, that would be the horizontal component, and then the magnitude times sine of the angle, that would be the vertical component. So this is all about working backwards, essentially. So earlier we had a position vector like this, and we were asked to find the magnitude and find the direction angle. So now, working backwards, if we're given the magnitude and direction angle, go ahead and write it as a position vector. So we do magnitude cosine of the direction angle, magnitude sine of the direction angle inside our angle brackets. Let's do an example of that working backwards idea. So we have vector W has a magnitude of 25 and direction angle of 41.7 degrees. Find the horizontal and vertical component. So we have this vector, we can see it here, although we don't really need the image, but we can see the magnitude is 25 and the direction angle is 41.7 degrees. So if we want to express this vector W in position vector form in angle brackets, we're going to take the magnitude 25 times cosine of the direction angle, comma, the magnitude sine of that direction angle, again 41.7 degrees. And this should be familiar in the sense that we already associate x, or a first coordinate, with cosine and the second coordinate with sine. And then we'll go ahead and multiply these values together and approximate here. So this is approximately 18.7 and 16.6 as a position vector. Alright, so we're going to go ahead and do that a few more times. Find the horizontal and vertical components to write each vector in the form AB as a position vector. So we have our vector u here, and we see that the magnitude of u is 5, and the direction angle here is 60. So we're focusing on these two pieces of information. So u is 5 cosine 60 degrees, and then 5 sine of 60 degrees. So those are angles we should know, so we're going to have 5 times 1/2 cosine of 60, and then 5 times radical 3 over 2. So in simplified form here, we'll go ahead and write 5 over 2, 5 rad 3 over 2. And what we really did there was essentially we're finding the coordinates of the terminal point. So we're finding that that terminal point is the point, so I'm going to change it to parentheses, 5 over 2, 5 rad 3 over 2. So that being said, we're looking for vector v. Vector v has a magnitude of 2 and a direction angle of 180 degrees. And we could absolutely use the formula, but if we understand the concept, this is a much quicker problem because we're really looking for the terminal point of my vector. And for this example, the terminal point is over here at -2, 0. So as a position vector, v is -2, 0 as its horizontal and vertical component. Now we could have used the formula, the magnitude times cosine of 180 degrees, the magnitude times sine of 180 degrees, but it's just a lot quicker if we understand the concept. And finally, for this last vector w, we have a magnitude of 6 and a direction angle of 280. So we'll go ahead and do 6 cosine of 280 degrees, 6 sine of 280 degrees, which are values we can't evaluate without a calculator. So it would be approximately 1.04 and -5.91. And our answer should make sense in the context of the problem, and we can see the vector is down here in quadrant 4, so we would be going over about 1 and down about 6. So we can see it matches the values we obtained. Now let's take a look at special vectors called unit vectors. A unit vector, u, has magnitude 1. So we have u inside these bars is equal to 1. And that should remind you of the unit circle with a radius of 1. Now we have these things called special unit vectors. So if I see a bold I, or the vector I, that's the vector 1, 0, and j is the vector 0, 1. So if I were to graph those unit vectors, those special unit vectors, so here's my xy plane, and I'm going to have 1 on the x-axis and 1 on the y-axis here. So the special unit vector I starts at the origin and ends at the terminal point 1, 0. So this is my unit vector I, and then the one that goes straight up is my unit vector j. And the reason why we have these unit vectors I and j is to create an alternate notation for vectors. So given vector v is the position vector a, b, and angle brackets, then instead of using angle brackets, what we can do is we can use this I and j notation. So v is also equivalent to a times the unit vector I plus b times the unit vector j. And we'll prove that these are the same things right now. So let's go ahead and write this as a times the unit vector I is 1, 0, plus b times the unit vector j is 0, 1. And since a and b are scalars, they can multiply to each component. So we'd get a 0 plus 0b. And then we can add each component, so we arrive at our notation with angle brackets a, b. So these are exactly the same, represent the exact same vector, but just alternate notation. So in this example, we want to write each vector using ij notation. And this ij notation actually often comes up more in physics classes, but you'll see it as I hat, j hat. So you'll see it with like a little hat above each one. We're going to go ahead and use the little vector arrow over each one though. So here, it's meant to be a pretty quick example. Instead of angle brackets, 2.5 and -4, using ij notation, this is equivalent to 2.5 I, and then it would be plus -4, and then my unit vector j. But we don't have to write plus minus. We can just go ahead and write 2.5 I minus 4 j. And then let's go ahead and take a look at this vector here. So we can see this is a position vector, starts at the origin, and it ends at the terminal point. So this point over here is -3, -2. So this vector is -3, -2 in angle brackets typically. To express it in ij notation, we're going to have -3i minus 2j. And it seems easy and straightforward right now, but students get really confused and mix up ij notation with angle bracket notation. So my warning here is that when using I and j notation, there should not be any comma. There should not be any comma, or there shouldn't be any angle brackets. There shouldn't be any comma and there shouldn't be any angle brackets. So what I mean by that, and I'll do it in red really quickly, is that I have students like mix things up and they'll put like -3i comma 2j. And that's completely incorrect. I cannot ever have i's and j's when I have angle brackets and commas. So two completely different notations. So I shouldn't ever see commas and angle brackets alongside i's and j's. So now in this next example, we're going to perform some of the same operations we did earlier, but now just using vectors in ij notation. So we have these three vectors given here, u, v, and w. And here we're asked to find u plus v. So we are asked to find adding 2i minus 3j, so that vector u plus the vector v, -i plus 4j. And we still add the components. So we're going to add 2i and -i, so that's going to give us just I. And then -3j plus 4j, so that's just plus j. So essentially it looks like we're adding like terms together. In example B, we're going to throw in some scalar multiplication here. So we have 3 times the vector w, so that's 2j, minus the vector u, so that's 2i minus 3j. So here we're going to multiply the 3 times 2j. So notice there's no horizontal component, there's no I component, so that means it's like a 0i, so we're essentially like ignoring it. So here what we have is we have 6j, and then this minus would distribute to both terms, so we have minus 2i plus 3j, and it's like adding like terms. So we're going to keep the I component first, so -2i, and 6j plus 3j is plus 9j. And using those same vectors again, we're going to find each of their magnitudes. So the magnitude of u, we're going to take the square root, and we just take the numerical values. So we're going to have 2 squared plus -3 squared. We don't take the I and j along with it. So we have the square root of 4 plus 9, which is the square root of 13. For part D, we're going to take the magnitude of v, so we're going to take the -1 and the positive 4. So we have the square root of -1 squared plus 4 squared. So 1 plus 16 is the square root of 17. And for the vector w, the I component is 0. So we would have the square root of 0 squared plus 2 squared, or the square root of 4, which is just 2. So we have that the magnitude of 2j is 2. And if we think about that graphically, so the vector 2j would be located going straight down to the coordinate 0, 0, -2. So if I think about the magnitude is the length, so that's why we keep just positive 2 as the magnitude of the vector. So if we're missing the horizontal or vertical component, then the magnitude is really just the coefficient of the unit vector I or j. Alright, so we just practiced with addition, subtraction, and scalar multiplications, the operations we have looked at so far with vectors. Now we're going to look at what's called the dot product for vectors. So given two vectors v and w, the dot product v dot w is equal to taking the horizontal components a and c and multiplying them, so a times c, plus taking the vertical components b and d and multiplying them. So AC plus BD is the dot product. So let's go ahead and find the dot product for these two vectors here. So we have v dot w is equal to 2 times negative 3 plus negative 4 times 0. So we end up with just negative 6 as my dot product for the first two vectors. In part B, we have two vectors, but this time in ij notation. So we're going to go ahead and apply our formula for the dot product. V dot w is going to be negative 1 times 2. So we're going to have negative 1 times 2 plus 3 times 1. So we're taking, again, just those numbers in front of the I and the j. So we have negative 2 plus 3, or just 1, as my dot product. So what's unique, what's different, is that the dot product result is a scalar. It's not a vector. So when we added two vectors, we got a vector, or subtracted two vectors, we got a vector. When we multiplied a vector by a scalar, we got a vector. But this dot product gives us out just one number, or a scalar. Parallel or orthogonal. Two vectors are called parallel if one is a scalar multiple of the other, or if v is equal to sum k times w. Two vectors are called orthogonal, which is a fancy way of saying they are perpendicular, they meet at a right angle, if their dot product, v dot w, is equal to 0. So this is one application of the dot product. In this example, we want to determine whether the following vectors are parallel, orthogonal, or neither. So if I look at these vectors, v equals 3i minus j and w equals 6i minus 2j. The first thing I want to do is determine if one is a scalar multiple of the other. So what I'm looking at is component-wise, is it the same number that I would multiply by to get from one component to the other first component? So here, in other words, to get from 3i to 6i, I would multiply by 2. And to get from negative j to negative 2j, I would again multiply by 2. So what that means here is that w is equal to 2 times v. So I'm just doubling each component from the original. So they are scalar multiples of one another. So that means that these two vectors are parallel. So I would say it's best to check in order whether the vectors are parallel first by determining if they're scalar multiples of one another. If they are, then we stop. They're just parallel. If that doesn't work, then we'll check their dot product to determine if they're orthogonal. And if neither of those work, then they're neither, because vectors don't have to be either parallel or orthogonal. Alright, we're going to do the same thing here, determine whether they're parallel, orthogonal, or neither. So again, first we'll check whether or not they're parallel. So to get from negative 1 to negative 3, that would be multiplication by 3. But to get from negative 1 to 2, that would be multiplication by negative 2. So those aren't the same values, they're not parallel. So now we move on to check whether they are orthogonal. So we have to do v dot w, or negative 1 times negative 3, the first component's multiplied, plus negative 1 times 2. And so we end up with 3 minus 2, which is 1. So since this is not 0, they're not orthogonal either. So the answer here is that they are neither. And last example here, same set of instructions. So first we'll determine if they are parallel. So to get from 2 to 3 here, I would have to multiply by 1.5. So this would be times 3 over 2, in other words. And here, this second component, to get from negative j to 6j, it's times negative 6. So those aren't the same, so they're not parallel. I move on to the dot product, so v dot w is equal to 2 times 3 plus negative 1 times 6, or 6 minus 6, which is 0. So if the dot product is 0, then these are considered orthogonal vectors. And now we look at the angle between two vectors. So if u and v are non-zero vectors, then the angle theta, where theta is between 0 and pi, is determined by this formula. So cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. Or we could also just think about this as theta, the angle between the two vectors, is cosine inverse of u dot v over the magnitude of u times the magnitude of v. And what we're finding here is if I have two vectors, so we're saying some u and some v, we are interested in the angle between them. So this is this angle theta I'm in search of, and it has to be between 0 and pi, which is of course 180 degrees. So we're not looking for this larger angle out here. We're looking for the smaller angle between the two vectors, the one that's between 0 and 180 degrees. So in this example, we're going to find the angle between each pair of vectors and leave our answers in degrees. So this is really going to apply two different concepts. We need the dot product and we need the magnitude here. So I'm going to go ahead and go straight to theta is equal to cosine inverse, and then I'm going to leave kind of a big set of parentheses here. So in the numerator is going to be the dot product, u dot v. So that's going to end up being 2 times 1, there's a 1 right here, plus, there's a 1 right here, so 1 times 4, so that is my dot product, over the magnitude of each individual vector. So here they're called v and w, so in the formula they were u and v, but the magnitude of each individual vector. So we're going to do the square root of 2 squared plus 1 squared, and then times the square root of the second vector's values. So we're going to have 1 squared plus 4 squared. So what we're going to enter into our calculator is cosine inverse of 6 over the square root of 5, the square root of 17, or cosine inverse of 6 over the square root of 85. So we do multiply the components underneath radicals if we're multiplying two radicals. So this is what we'd enter into our calculator and approximate to the nearest whole number here. So this is approximately 49 degrees. So it's really just the dot product and then the magnitude formula for the given vectors. And we'll go ahead and do the same thing over here. So we have theta is equal to cosine inverse, and we're going to have the dot product. So 0 times negative 3 plus 3 times negative 3 over the square root of 0 squared plus 3 squared, the magnitude of the first vector, times the square root of negative 3 squared plus negative 3 squared. So this is going to simplify to cosine inverse of, in the numerator, a negative 9. In the denominator, this right here is just the square root of 9, so that's 3. and then times the square root of 18. So I can simplify this here. There would be a -3 on top. And so this value is exactly equal to 135 degrees. And to finish out, I just want us to think about why it's exactly that value. So if I graph each of these vectors here, so I'm going to just do a quick sketch over here. If I graph the vector 0, 3, that's going to go ahead and be straight up. So it's going to end at 3 here. And then the vector -3, -3, that's going to be over here in quadrant 3. So I'd go -3 left and -3 down. So if I think about this, the angle between the two vectors here, well, this is a 90-degree angle, and -3, -3 splits this quadrant in half, so this right here is 45. So if I'm adding my 90-degree angle and my 45-degree angle, that's exactly 135 degrees. So we may not have known that just looking at the vectors, but after applying the formula for the angle between two vectors, we can maybe see why that's exactly 135 degrees.